Okay, we're doing example 3 on section 5.2, more finding relative extrema. So again, the first thing that we always want to do is find the critical numbers to see where those max and min values might occur. So for this particular function, just realize that we might have that other kind of critical number here, that is where the derivative is not defined. One thing we might want to just make note of here is what the domain of this function is. That's a cube root, and so is that. So if you've got cube roots on both of these, it's okay to take the cube root of a negative number. So the domain of this thing is going to be all real numbers. So that's kind of something we might want to notice for later. So then next, we'll take the derivative of this thing using the power rule. So the power rule says, again, take that 2/3, put it in front, lower that power by 1. So 2/3 minus 1 is negative 1/3. And then minus, same thing here, bring that power down to the front, lower the power by 1. If I subtract 1 from that, I get 2/3. So there's my derivative. Let's go ahead and rewrite this so that it has a positive exponent there. This will be the same as 2 over 3 x to the 1/3 power minus 5/3 x to the 2/3 power. Okay, and then we're going to want to set this thing equal to 0 to figure out where those critical numbers occur. So before well actually, that's a minus. I think the best way to solve this is just to simply move that over to the other side. So we get 2 over 3x to the 1/3 equals 5/3 x to the 2/3. Okay, and to solve this equation, I think cross-multiplying is the best way to go. In fact, actually, that x to the 2/3, you could really put it up there with the 5. Same thing. So if we cross-multiply here, we're going to get the denominator here is 3, the numerator here is 2. We're going to get a 6. And then on the other side, this 3x to the 1/3 times 5x to the 2/3. So we'll get 5 times 3, and then we've got an x to the 1/3, and then we've got an x to the 2/3. We put all that together. So cross-multiplying again, just this whole thing, denominator here multiplied by the 5x to the 2/3. We can simplify this a little bit. That's going to be 6 is equal to the 5 times the 3 is going to be 15. When we have x's multiplied together like this with different exponents, the rule says that we have to add the exponents. So if we add 1/3 to 2/3, that's 3/3. So that's just 1. So we're just left with x to the first power there. And so solving that for x, we get x is equal to 6 over 15. Okay, well that reduces, if we divide both of those by 3, we get 2/5. So 2/5 is a critical number. That's a place where the derivative is 0. Now on this particular problem, on this particular function here, so this is a critical, I'm going to call this the type 1 critical number. I don't know if the book separates these by types or not, but really what I call the type 1 critical number is the type where the derivative is equal to 0, and that's what we just solved for here. There's another critical number on this function, though. If we look back up here at the derivative, here it is, there's the derivative. Notice that if I try to plug 0 in there, I'm going to have a problem. The derivative is actually undefined there, but that is the derivative. If I plug in 0, I'm trying to divide by 0, that doesn't work. So 0 is also a critical number. And that's a type 2 critical number. And type 2, again, this is sort of my own definition here. Type 2 critical number is the one where the derivative is undefined. And I think you don't really need too much explanation about why that's undefined there. It's just dividing by 0, right? If x is 0, then you've got a problem. Okay, so we've got 2 critical numbers. Now we'll do what we did in the last problem. That is, we're trying to find the minimum and maximum values here, all the relative extrema. So we set up our table. We say minus infinity up to the smaller of the two critical numbers. In this case, that's 0. And then we go from 0 up to the next critical number, which was 2/5. And notice this is kind of why we wanted to have the domain up here, because if the domain was not all real numbers, then of course we wouldn't want to be starting at negative infinity here. We'd probably want to be starting at the smallest value of the domain. Okay, so then from 2/5 we'll go up to the other end of the domain, which is positive infinity. So notice the way we're always doing this. We find the critical numbers, we set up this table, go from the left of the domain to the first critical number, and then that critical number to the second one. And we just keep doing that for as many critical numbers as we have. And then we end at the other end of the domain. Okay, in this case, positive infinity. Okay, so now we make our table. And we're going to pick our test values, just like we did on the last example. It's pretty much the same way every time. We want to figure out what the sign of the derivative is. So sign of f prime. And then we want to, based on that, see what's happening with the function. And remember, the way that we can tell that we have a minimum or maximum value is if the sign of the derivative changes on either side of the critical number. So let's pick -1. Let's pick, we're going to have to go pretty small on that. Smaller than 2/5, but bigger than 0. Not too much choice there, but we'll try 1/5 there. And then bigger than 2/5, let's pick 1. Okay, so what we're going to do again with these numbers is we're going to plug them into the derivative. Okay, so 3 numbers, plug them, there's the derivative, that's what we want to plug them into. So this one is not maybe so obvious what's going to happen here. If we plug in, let's start with 1 here. If I plug in 1, then I'm going to have just 2/3, because the 1 to the 1/3 is just 1. Same with 1 to the 2/3 is just 1. So we're going to have 2/3 minus 5/3. So 2/3 minus 5/3, that's definitely going to be a negative number, right? 5/3 is bigger than 2/3, and so we're subtracting it, so we're going to get a negative there. Now notice what happens when I plug in -1. When I do -1 here, -1 to the 1/3 power, that's the cube root of -1. So that's negative. Okay, so I'm going to have a negative 2/3 if I do that. And then if I plug in -1 here, notice what happens. I'm actually squaring it, because that's the numerator being a 2 there means the second power. And then I'm taking the cube root of it. So if I got -1 squared, that's 1, and then the cube root of 1 is 1. So that ends up actually also being negative. It's a minus right there. So I got a minus and then another minus. So that's negative as well. And then for, oh, sorry, I put that in the wrong place. That should be for -1 is the one we just plugged in. Fix that. We just did -1, not 1/5. So that is the one that's negative. And then lastly, if we plug in 1/5, I think what we're going to find, and you can verify this, if we plug in 1/5, what we get, it's going to be some decimal here, it's going to be some decimal there, but just go ahead and verify this on your calculator. What you're going to find is that it actually is positive there. Okay, so again, all we really care about is what is the sign of the derivative. So once we plug that test value in there, what kind of number do we get? Is it positive or is it negative? So again, I think you'll find if you plug that in, you're going to get a positive number there. So what does that tell us? That the function is decreasing on that entire interval, and then it's increasing, and then it's decreasing again. Okay? So once again, we find that the derivative changed sign at a critical number. Okay? So what does that tell us? It tells us that since it changed from decreasing to increasing, that it was decreasing before, then it was increasing after, that tells us we've got a minimum value. So we've got a minimum value at x equals 0, or if we want to be specific about it, 0, f of 0. Now f of 0 is actually easy to find, because if I plug 0, again, remember we're putting this back into the original function. 0 to the 2/3 and 0 to the 5/3, they're both 0. So this is actually just 0, 0. So we've got a minimum value there. And then we have a maximum value, since it changes from positive to negative here, from increasing to decreasing, we've got a maximum value at 2/5, that was the critical number, and then whatever f of 2/5 is. that one we'll have to figure out. Okay, but remember, we always want to figure out what that y value actually is. Since I'm running out of room over here, I'm going to put the f of 2/5 over here. So what is f of 2/5? Again, I've got this in my calculator, so I can just plug it in. Of course, you hopefully have a calculator as well. You can use that, of course, to figure out what these values are. Okay, so this one actually ends up being a bit messy, so let me just do a decimal on this one. So we're going to get, for 2/5, 0.326. If you want the actual value here, let me see if I can get my calculator to make it look a little bit simpler. Let's see. Yeah. Well, anyway, it doesn't look very nice. It's like 3 times 5 to the 1/3, 2 to the 2/3 over 25. So if you're interested, this is the value that I'm getting from my calculator. It's 3 times 5 to the 1/3. It's the cube root of 5. And then 2 to the 2/3. And then over 25. So if you have to enter this into MyMathLab as some similar question like this, you'll want to enter it like that because that's the exact value. So anyway, our max value occurs at, let's see, I don't think I have room there. So the maximum occurs at, the exact location is 2/5, and then we'll just use that decimal, 0.326. And again, if you were to actually graph this function on your calculator, you should notice that that's exactly what happens. We've got a minimum at 0, 0. And since that critical number was one of those type 2, that means it's got like a sharp point there. You should see kind of the graph going down, sharp point at 0, then it sort of comes back up. When it comes back up, then it'll reach a maximum at 2/5, and then it'll start to go back down again. So there we go. So this is sort of maybe a little bit more difficult than just a polynomial function, but anyway, this is the way that we approach these types of problems for critical numbers and max and min values.